A very good afternoon to all of you. It is my honor to introduce this session's keynote speaker, Professor Katarzyna, on the topic Federated Learning in Internet of Things Ecosystems, Perspectives and Challenges. Professor Katarzyna is an assistant professor at the Systems Research Institute, Polish Academy of Sciences, data and business architect, intelligence architect at Pentasoft System Informatization FA. An experienced practitioner in data engineering and analysis, data modeling, data warehousing, data mining, business intelligence, with over 15 years of experience in industry and research, IT practice, programmer, analyst, architect, team leader, and consultant. Graduated from Warsaw University of Technology, Faculty of Mathematics and Information Technology, and obtained MSc Engineering title in Computer Science. PhD thesis defended in Systems Research Institute of Polish Academy of Sciences. Scientific interests are artificial intelligence and semantic technologies and their applicability in various areas. Author of over 45 papers, a reviewer for Computer Science and Information Systems Journal, IEEE Transactions, Internet of Things Journal, Journal of Network and Computer Applications, Journal of Intelligent Information Systems, active member of Polish Information Processing Society and Chair of Computer Science and Systems Track of Federated Conference on Computer Science and Information System. Yearly international multi-conference with more than 250 participants from over 40 countries. Executive editor of Scalable Computing, Practice and Experience Journal. So I hand over the session to Professor Katarzyna. Okay, madam.
Yes, thank you very much. I'm sorry for the slight delay. Unfortunately, there are some technical problems from far away. Okay, I will share my screen right now with the presentation. I hope that you can see the presentation right now, the presentation mode, if you could kindly confirm.
Yes, it is visible.
Okay, so I would like to devote my presentation today to the topic of federated learning, specifically in the area of Internet of Things that is on the rise right now. So there are many challenges, many perspectives related to that. And this is also the research area that we are dealing with in Science Research Institute of Polish Academy of Sciences, where I am part of the team working on these topics. So to start with, I would like to say a few words about the vocabulary that is related to intelligence and to learning, and that has been on for some time right now. There are a lot of terms being used that are quite close, but the meaning is not interchangeable, so there are slight differences. So first of all, we can talk about distributed intelligence. This is a general top-level terms that actually has two meanings depending on the context. So it can be either collective intelligence or distributed artificial intelligence. And with collective intelligence, what we mean is the intelligence that emerges from collaboration and competitions of multiple individuals. So here we deal with the different aspects of decision making, of reaching a consensus. We use mechanisms such as cognition, cooperation, coordination. Then on the other hand, distributed intelligence can have a meaning, distributed artificial intelligence or decentralized AI. And in here we mean a subfield of AI that is dedicated to development of some distributed solutions to problems. And this field of research is also treated like a predecessor to the research devoted to software agent, to multi-agent systems. So distributed problem solving here. Distributed artificial intelligence very often are systems that consist of some autonomous nodes that we tend to call agents. They have some characteristics, like they can act independently while communicating. Very often in such systems, the nodes are loosely coupled, slow, robust, flexible. Such systems are designed to provide adaptability to changes when it comes to the problem definitions and data set. And now the area, the field that is of specific significance to our work is actually distributed program solving within DAI, so distributed AI, and specifically within distributed machine learning. And here the assumptions are a bit different. So the DAI or distributed problem solving, it does not have to be related strictly to software agents. It can involve solving problems in any distributed environment. And the focus here is put on how to effectively and efficiently use resources available in the ecosystem. So here we also use concepts that materialize outside of distributed artificial intelligence. So the concepts related to grid computing, fog computing, or edge computing. Now, within distributed artificial intelligence, we have distributed machine learning. And distributed machine learning, this is field very related to our work. So in distributed machine learning, we assume that we have a computationally intensive task. It is related to artificial intelligence, to ML. It can be the task of training a neural network or some nature-inspired optimization, and it simply needs to be completed. Very often for this task, we have a large data set so that completing the task on a single computing node can be problematic in terms of time that is required, in terms of resources that is required. But on the other hand, we may consider that we may have multiple computing nodes available. So the research question is how to distribute the work, how to later combine the results, so how to create some subtasks, execute them internally, and then aggregate the results coming from that subtask. Actually, distributed machine learning, this is not a new field of study. It is well studied. It is based on RDS from parallel computing. This is a very major research area. So there is over 40 years of development in that area. However, even though it's very major, right now it's some assumptions or some context, environmental information surrounding this research has simply changed over the last few years. So first, based on what was usually assumed and considered or stated in classical DML. So first of all, there was an implicit assumption that there is a single stakeholder data owner, single user owner of the data, and the data could be distributed to complete machine learning, still remaining out under the full control of its owner. Then also it was often considered that open source public data set can be added to augment the training. And this is in terms of practical real-life deployments a bit assumption that is a bit simplifying the problems or omitting a bit several surrounding problems. However, this approach works well with cloud computing. Usually here cloud provider can guarantee full control over data. But with time, some new changes related to data, related to needs started to appear and need to be recognized also in that field of study to be properly addressed. So looking not only from the more algorithmic side, but also from the perspective of in what environment, in what context, and infrastructure we need to apply the solutions, it should be recognized that right now what we are dealing with is the proliferation of data. So we have smartphones with multiple sensors that generate streams of data that we may want to control and use. This is also stimulated by the fast drop of prices, sizes of sensors, actuators. They can be placed anywhere, can belong to anybody. Moreover, there is ease of communication. So with availability of networks with various bandwidth ranges, we can set up easy communication between sensors, actuators, edge devices, computing nodes, gateways, so all kinds of nodes that can be used in such a distributed systems. Important is to recognize that the problem right now that we need to address is that users have data, but actually we are very often lacking, or we need to deal with the problem of providing capabilities to process the data. Another thing is that data covers only fragments of possible domain of interests. So we may have data, parts of the data belonging to different subjects gathered by different organizations, and the real value, the real valuable service may be achievable when considering combined data streams and not only individual data streams. Now, when it comes to the processing side, so it needs to be stated that there is a real progress and more applicability on solutions based on the concept of Internet of Things. Internet of Things meaning smart everything. So a lot of devices that we can connect to the network that can exchange information and actually form a really distributed computing evolving infrastructure. And here what we should consider is that actually having those changes in mind, we should rethink, update the ML data analytics methods also to match those new application areas. The changes are happening, so we have ML dedicated hardware that is available, but also another thing that needs to be considered is that the vision of single owner of data used specifically in ML to train models is not longer valid. So we need to deal with a multi-tenancy, multiple stakeholders, data ownership, and adapt the processes, the protocols accordingly. So in a nutshell, the challenges right now that we are having and that research is focused on is to address issues such as having multiple devices that have data that is valuable only if combined, that we deal with data sets that are many of them and they're large, so it may be problematic to transfer them to the cloud or to some central location. Another thing is that these local data may not be allowed to leave the location due to some confidentiality policies. On the other hand, they may belong to different stakeholders, different companies, so there can be some IPR restrictions also related, and this is something that we need to recognize. So also focus and have a look onto the let's say practical aspects of executing distributed AI. Now, here, what comes to the rescue is the concept of federated learning. So federated learning is the approach to machine learning where training of model involves multiple data sets that are stored in local nodes, and training does not involve exchanging the data itself. So the goal here is to train central shared models. We have participating nodes that use local data to train some subversion of the model, and then the local parameters are sent and combined in a central model. So there are updates happening, there are aggregation happening, and after the updated central model, it can be redistributed back to participating nodes. And such process is repeated until good enough quality is achieved. Of course, some further local training, some personalization is still possible. So this is the procedure that can be applied. And now, what are the difference between federated learning and the classical distributed machine learning? Very top level differences. So with distributed machine learning, the focus was, or the implicit assumption was, that we have single data owner, that data are available to processing nodes. So simply the issue is to have machine learning software at each node, and then to distribute the problem, distribute the data. The data exchange of information was assumed to be executed, performed as needed. So no special interest or focus was put on security, privacy, or trust issues. So the research was focused on different aspects, more on distribution, on aggregation, how to optimize this. With federated learning, the research focus shifted into a bit different aspects. So here we consider by design multiple data owners. We consider the fact that data is private and is not to be revealed, so it should stay in the even in its original location at local nodes. Only proposed model updates are communicated, so we communicate only what is necessary, and also security, privacy, trust. These are the issues that, because of the aforementioned, needs to be taken into account, and solutions need to be proposed also here. Now, when we talk about federated learning, it's not one specific type of solution of system that we may provide, but actually they can be different version and different times. And in the paper called A Survey on Federated Learning Systems, Vision, Hype, and Reality for Data Privacy and Protection, here authors proposed a very nice and useful taxonomy of federated learning systems. So we may have some dimensions to describe such systems that we should consider, that we should find or answer which value is taken for each of these. And based on this, we may adjust, we may consider what it's the structure of the federated learning solutions that we need. So very briefly, the vision here is with respect to data partitioning, which can be horizontal or vertical. With horizontal, the data sets of different parties available at different nodes can have the same feature space, but then little intersection on the sample space. With vertical, they have the same or similar sample space, but differ in the feature space. So this is the characteristics of the environment in which we want to adapt federated learning. When it comes to privacy mechanism here, by design, we should consider what we need. So we may include information encryption, some homomorphic encryptions, differential privacy, secure aggregation. There are different methods that can be applied depending on the needs, depending on the requirements. Then we should also think about the motivation for the federation that we want to do. So if it's based more on incentives or legal requirement, incentives is noticing or recognizing the fact that single owner data may be not enough. So cooperation is needed to achieve better common goals. Legal requirements means that we need to consider federated learning solutions because of some privacy, security, restriction obligations that we need to follow. Then when it comes to the communication architecture, we may go in two directions. So we may consider under either centralized architecture when there's a manager that aggregates the information, updates from nodes sent back to the set training results, or we can consider methods for federated learning that are decentralized. This means that communication are performed among nodes, and not every and actually every party can update the global parameters, so it's more like a peer-to-peer approach. Then when designing such a system, we should also consider a scale of federation. So if we are considering a cross-device or cross-silo. Cross-device means mass number of devices. When we have stateless clients that are not very reliable clients, so they may appear, disappear, the result may be provided or not. Here security and trust issues are important because of the number of such devices. The communication can be a bottleneck, and usually what we are doing here is also a central orchestration in such approach and horizontal partitioning. With federation being cross-silo, here we consider limited number of clients, usually between 2 and 100, that usually all are participating in the training process, and they are treated as reliable clients. So they are more controllable, more predictable. Here security trust can be easier to manage. We can consider different orchestration model. And in cross silo, simply the clients are bigger, more stable, and there's limited number of there. Now, with federated learning, there are different applications areas right now, more and more because of the characteristics that I talked about. Just to name very few, we use federated learning very often in preventive maintenance. Situations when machines belong to independent owners, we don't want to share data with the competitors. However, to improve larger models for better machine maintenance with better results, better value of the quality metrics, then the goal is to combine what we have locally with other parties. Another area is pharmaceutical companies, and here very often we also do collective training on private data sets. For example, for drug discovery, there's a platform that is quite well known. It's called Melody. Right now, what is also being considered is the use or application of federated learning along with the concept of the Internet of Things that I was talking about. So Internet of Things is the next generation type of architectures that we have when building our systems, recognizing the need to distribute, to massively process, to have communication, and it goes very much in line with the concepts that are behind federated learning. So any ideas joining those two are gaining on popularity. The rising popularity of federated learning can be also seen when analyzing and going through platforms that are available. So just to name the few that are most important, they are listed here. You can see that there's a lot of them. They have different level of maturity. They are focused more on or better for research purposes. Some of them are better for production. They're the ones that are more concerned about security, privacy, data confidentiality, the ones of them that are more focused on supporting more ML models. As you see, the development is ongoing, and this is also the step ahead to somehow standardize and prepare federated learning to be well documented, well designed solution going outside of the academics, also into the production and industry. Now, a few words about the project that we at SRIPAS participated in. So it's Assist IoT project. This is the project that is committed to creation of blueprint decentralized architecture for next generation Internet of Things. Here we have a decentralized approach when we prepare components that can be deployed on edge, even far edge. We use support from cloud when needed, so being also in line with the concept of some edge cloud continuum. And we, in this project, we are dealing with several aspects that need to be considered. So besides working on distributed networking components, some decentralized security, privacy, what we are also doing is smart distributed AI enablers. Besides self-style capabilities, human-centric tools. So we prepare solutions called enablers to cover different needs that can be positioned on a planes, among which we identify device and edge, smart networking, data management, application and services plane. And on the other hand, we also considered verticals that are cross planes and provide solutions related to manageability, scalability, security, privacy, trust, interoperability, and self-start. And among the different solutions and consideration in the project, what we were also working on and are still working on is the federated learning architecture that is composed of several enablers that can be deployed in line with the concept presented by Assist IoT reference architecture to provide the infrastructure, the backbone to execute distributed training or set up distributed inference capabilities in such IoT-based ecosystems. So we consider several enablers in the design. The ones that are very important here are FL local operations. These are the ones that are actually running on nodes or local devices, and they're perform the local training on the local data. Then there is the training collector enablers that is responsible for aggregation of the results coming from local operators. And there is also FL orchestrator, and this is the enabler, the component that is responsible for controlling the life cycle of such a job, for controlling the configuration and the setup of FL related jobs that needs to be executed. Additionally, we have FL repository, and this is the repository where we store algorithms, models, any auxiliary data that are required to be persistent for the sake of the process, and later on to be able to reuse the results coming from the federated learning procedures. So these are 4 types of enablers that we recognize and the functionalities that they are related to. However, another issue is that also using them as a component, as a building blocks, we can consider different topologies that can be represented in the federated learning system. So the basic one is simply the centralized topology with one training collector, one aggregator. However, normally we can also think about some hierarchical or other approaches. And the use case in the project where we are mostly dealing with federated learning, however, this is not the only use case where we applied. It's related to cohesive vehicle monitoring and diagnostic. Here, federated learning is applied as a part of car damage recognition pilot scenario. The goal is simply to provide fast, accurate inspection of car exterior and recognize damage, also with minimal transfer of data from edge devices to the cloud. And here, the use case itself is executed considering gates that are visible on the photo here, through which the car comes through, and there are cameras located at different positions that take pictures, and then what needs to be done is some AI-based automatic inspection of these acquired images. So we can consider having one such scanner. There can be several scanners in one institution, but this is our source of data. And now what we can propose for such a setup is that actually the local operations can be located on each specific scanner. So a scanner can be our node in federated learning that is that has access to those local images that were taken, and that can perform local training. And then the training collector, orchestrator, repository, these are components that can be located in a more centralized location, let's say in the cloud, to control the process and how it's going on. Here in this setup, we consider that local operations are on scanners, but one can also imagine a situation when we can go one, let's say, level deeper and consider specific cameras. Now, on the diagram here, we have the enablers the four federated learning related enablers. However, there are some more like authorization, identity manager, tactile dashboard. This is actually the benefit of developing our parts related to federated learning according to reference architecture of Assist IoT, so that we can easily integrate and reuse other enablers, other components that are available or were prepared in the IoT, Assist IoT, to finally deploy, prepare the whole, let's say, more production-ready solution, considering also additional functionalities such as dashboard or cybersecurity, so authorization, identity management that normally also needs to be considered if we want to apply federated learning in production. So looking from the perspective of the practical use case, there are some additional consideration that we need to take into account. So first of all, not only from this use case, but generally use case that we dealt with. What we need to deal with in federated learning, and that what may cause some additional problems that needs to be addressed, is the heterogeneity of clients and network that can cause delay. What also may we may encounter are interoperability issues. We may encounter weaker, more busy clients with different capabilities, so they can slow down, disrupt a bit the training process. Then, depending on the environment, we may have a weak network connectivity. So here some sudden dropouts may also appear. We may deal with some systems limitations, so number of cores, locally available RAM, the processing capability of different clients can be different. We also need to consider that we may want to use edge devices with very limited battery life, so this can have some consequences. For example, the use of large models may not be possible. They may have some restrictions also on training time. And there are many nearby research areas, such as data for the training that can be highly redundant. We also in federated learning should pay attention to the data distribution, the data characteristics, how it looks like on specific nodes, specific clients. Then, depending on the conditions, also when answering the questions or analyzing the federated learning taxonomy, we may choose the most appropriate topology. So the way that we connect the clients, the nodes, how we organize the aggregation. So in our case, training collectors to best fit the need of a specific use case. Also, what needs to be considered and very often is not paid too much attention is the need for data pre-processing. So normally in machine learning, we very often have a need to do some pre-processing. And this is something that needs to be taken care of, put somewhere in their architecture, have an appropriate component places in the pipeline to consider this. And finally, security, privacy, the level that we want to achieve, the mechanisms that we want to include. So as you can see, besides classical algorithmic approach, distribution, focus on aggregation, there are a lot of more engineering related practical problems, also dealing with system design that needs to be considered. When it comes to work of our team, we are continuing the work on the concepts related to federated learning, to distributed AI in another Horizon 2020 research project. This one is called AROS. And here the project generally focuses on transparently utilizing the resources on edge to cloud computing continuum for enabling application and also while incorporating some multiple services. Within this project that is large in scope, we are dealing with explainable, decentralized, frugal AI. So besides working on the infrastructure, the backbone to execute federated learning, what we also want to consider is how we can recognize the requirements and address them when it comes to frugality. Frugality meaning limited data availability, limited processing power on memory when we need to adapt the solution to such a situation, and also to what extent, going how far into the edge or where in the edge cloud continuum we can include explainability mechanisms that are right now also intensively studied, because in many critical let's say data or applicability areas, the systems need to be explainable or at least interpretable to be considered for production. So to sum up, federated learning, it's right now popular, important research directions. However, it needs to be recognized that we should also have in mind that some real-life constraints need to be considered, relate to practical use cases, relate to designing the solution as a whole. It can be very well combined with the research that is happening in edge computing, in Internet of Things. These two paradigms, these two approaches combine together well, and some challenges here are common. When it comes to federated learning itself, it is quite broad. It can be applied to basically any ML approach. The condition here is that it should be distributable. Area still very open in research questions. There is the publication advances and open problems in federated learning, when you can briefly see what is there still to be studied and what questions still remain open. And that's all when it comes to my presentation. If there are any questions, then you are very welcome